Hello class, this is Mr. Hart, and this podcast we want to start the unit on center of mass. Okay. Now you may be wondering, why is the center of mass important? It's just something we calculate and then we never think about, but it's actually really important to physics and describing a lot of scenarios. Okay. Let me show you a demonstration I usually do at the start of class. This is a video of me doing that same demonstration, but you can see by this little ramp that I've made that obviously most things just roll down the ramp as would be expected, but when I put this cone on the ramp, something weird happens. Okay, it starts to roll uphill, okay, to those little notches. Okay, and that's really odd behavior. Okay, so is gravity broken? Okay, well, to answer that question, we'll need to answer that a little bit later when we understand a little bit more about the center of mass, but we will come back to this later on. Okay. So in class, we show a video by Derek Mueller of Veritasium, and he basically asks a very simple question. How will a slinky fall? Okay, you leave it stretched out like this, and you intend to drop it. Okay, how will it fall? Will it stay stretched out, or will it come to the top, or will the bottom and the top meet? Okay, and specifically, it gives these four options. Okay, so when you drop that slinky, does the bottom go to the top of the slinky and then it falls? Or does the top go to the bottom of the slinky and then it falls? Or will it just fall stretched out? Or will the top and bottom meet in the center somewhere and then it falls? Okay, so take a second and think about how you would answer that question. Okay, you might be surprised by the answer you get. Okay, now if you thought about it long, most students usually end up on this answer. Okay, D, that the top and bottom meet in the center, but that is actually not the case. Okay, here is a video of me performing that same experiment in slow motion. Okay, and I don't have a great slinky, but hopefully you can see that in this video the top goes to the bottom first and then it drops. Okay, now that's kind of crazy. Okay, the bottom's just sitting there, it's not moving. Okay, how is gravity not pulling the bottom of the slinky down? Okay, so in other words, how in the world can this be? Okay, did gravity break again? Well, what's going on? Okay, and so to answer this question, we need to understand the center of mass and why it's important. Okay, so Newton's not wrong. Okay, he knew what he was doing, but here's the underlying assumption we've been having with most of Newtonian physics. Okay, so the underlying assumption of Newtonian physics is all object movements are determined for the center of mass of the object. Okay, when we're doing these equations with force and energy and things like that, we're determining it for the center of mass. Okay, those kinematic equations are for the center of mass because we can't represent the whole object every time. Okay, it's really hard for like a human body, for example. How would you represent that mathematically? Okay, you got differing lengths, right? Different appendages you'd have to account for. It's really difficult to work with those situations. We can do it computationally sometimes in the very high level physics, but for basic level physics, that's really hard to deal with. Okay, so we're using the center of mass as our reference point when we do those equations. Okay, so before we go on and describe how that solves some of these problems, let's just look at what is the center of mass, how do we calculate it. Okay, the center of mass is described in this way. It's the point at which mass is equal on all sides. Okay, so for a human person, we're vertically symmetric, right? Okay, you could draw a line of symmetry down us and we'd be equal on both sides. So our center of mass is going to be somewhere along that line. Okay, now we're not, horizontally symmetric, I guess, right? Your legs are not the same size as your head. Okay, so it ends up usually being somewhere around your like lower chest area, or your stomach is your center of mass. Okay, but it's where the mass should be equal on all sides for a person. Okay, or any object in that case, okay, where all the mass is balanced. So mathematically, we describe it this way, and we calculate it this way. Basically, the distance or position, okay, the position of the center of mass, okay, so we call it x-com or x subcom. So in this case, we're only working in one dimension, but you can imagine a similar equation for two dimensions. But in one dimension, it's just the mass of the first object that you're dealing with times the position of that first object, times the mass of the second object times the position of the second object, okay? And add as many objects as you have, and then divide it by the mass of all the objects added together, okay? So, for example, if you had a person, we don't have separate objects we're dealing with, but you could imagine doing it with like appendages. You could do the mass of your arm times the relative center of your arm plus the mass of this arm times the center of that arm plus the mass of your head times the position of your head, okay, and so on and so forth. And you could use that to determine the center of mass, okay? Let's do an example problem and see how this works out, okay? So here's a very simple example, okay? So we have basically a dumbbell, okay? It's a lopsided dumbbell, so you have a big, huge mass on this side, but you have an even larger mass on that side, okay? And you want to determine the center of mass, okay? So we have some options in this case, but basically we'll say the center of mass position is equal to mass 1 times position 1 plus mass 2 times position 2 over mass 1 plus mass 2, okay? So in this case, mass 1 is 5 kilograms, and its position is 0, okay? That's going to be nice because usually that means we don't have to add it to anything. It just cancels out. And then mass 2 and position 2 is 4 and 15. Okay, and divide that by the sum of the masses, which is 5 plus 15, which is 20. Okay, so in this case, 5 times 0 is 0, 4 times 15 is 60, and then the bottom was 20, so 60 over 20 is going to give us 3 meters. Okay, so if this is 4 meters long, okay, 3 meters would be about right here. So if you took that dumbbell, and if you could balance it on your fingers, I don't think you could balance 40 pounds on your finger, but if you could, okay, you'd place that right about there, and it would balance, okay? That's another way to determine center of mass without an equation. Have any object, you can just kind of put your finger like this until it balances, and that's your center of mass, okay? So my pen, for example, center of mass is about right there, okay? I'm not perfect, but it'll be around right there, okay? You can determine that with any object if you can balance it that way. It's a good way to determine the center of mass, okay? All right, let's do a couple more examples mathematically, okay, of determining the center of mass. So 2 objects are 4 meters from each other, okay? In this case, the first object has a mass of 15 kilograms. The second object has a mass of 20 kilograms. What is the center of mass of the system? Now notice in this scenario, they don't specifically say one object's at 0 meters, one object's at 4 meters. They don't give specific positions. So usually what I do is, if it's not stated, they just have a total distance, then I usually just assume the first mass is at position 0. Okay, so we get that XCOM, or center of mass, equals mass 1, which is 15, times position. Doesn't state it, so I'm just going to assume it's at 0. Okay, and mathematically we can do this. Okay, and we add that to mass 2 times its distance, which is 4. Okay, and then we divide that by the total mass, which is 20 plus 15. Okay, 15 times 0 gives us 0. 20 times 4 gives us 80. And then the bottom gives us 35. Okay, we put that in our calculator. And that gives us 2.29 meters. Okay. Or in other words, you'd want to put your finger 2.29 meters away from the first mass, and that would be the center of mass. Okay. When we find XCOM, or the center of mass, it's always from reference from the first object. Okay. All right, let's do one more, and then we'll look at some of the phenomenon that occur because of this. Okay. Here's one more scenario. So 3 painters stand on a paint scaffolding that's 5 meters across. The first person has a mass of 80 kilograms and is standing on the left edge. The second person has a mass of 50 kilograms and is standing on the center. And the third person has a mass of 70 kilograms and is standing on the right edge. Where is the center of mass of the system? Okay, Notice again, no specific distances are given, but we know that the total scaffolding is 5 meters across. I'm just going to state that this is 0 meters, okay, on the left side, and that would make the center 2.5. Okay, now we can kind of assign the masses and positions. So the first person was standing on the left edge, and he was 80 kilograms. The next person was 50 kilograms standing in the center, and the last person was 70 standing on the right side. Okay, so now we kind of have our setup of the different people where they'd be standing. Okay, now we can calculate XCOM. So XCOM equals mass 1, which is 80, times its position, which is 0. Again, that's nice because that just gets rid of it. Next person was 50 kilograms, and they were 2.5 meters in. Last person was 70 kilograms, and they were 5 meters in. And then the masses are 80 plus 50 plus 70. Okay. I'm not going to take the time to simplify that, but if we put that all in our calculator, then we get, when all is said and done, that the center of mass is 2.375 meters. Okay? Or in other words, okay, it's right to the left of the guy standing in the center. Okay, so the center of mass in this system would be about right here. Okay, it's almost center, not quite, but that's where the center of mass would be for that paint scaffolding. Okay, but there you go. That's how you calculate the center of mass. Okay, pretty easy. Just gotta know where your masses and positions are. Okay, all right. Let's look at what happens because of this. Okay. So keep in mind, we said before that our movements were calculated for the center of mass. So if we go back to my first example, okay, with the Slinky Drop, okay, it says the center of mass of the Slinky will fall at gravitational acceleration, okay. Now we usually say an object will fall at gravitational acceleration, but now we're being a little bit more specific. The center of mass of the Slinky will fall at gravitational acceleration, okay. Let me demonstrate this with a video I made, okay. So in this video, same scenario, dropping a Slinky. We'll watch it fall to the bottom first, but now notice that the pen is at the center of the Slinky, and it falls at the same rate that the Slinky does. Okay, so the center of mass of that Slinky and the center of mass of the pen, which is pretty much just the pen, hit the ground at the same time, and thus have the same movement according to Newton. Okay, that's pretty cool that we can show that the Slinky, even though it doesn't behave like we would think, its center of mass still behaves according to Newtonian physics. Okay, that's cool. Okay, let's think about some other scenarios that come because of the center of mass. Let's think about a firework, for example. Okay, we have this kind of key concept that the center of mass behaves according to Newtonian physics. Okay, well, guess what? Even fireworks, big, huge explosions, something happens in the middle of the air, guess what? They still behave according to Newtonian physics. And you may be thinking, what? How is that even possible? Okay, but if you think about a firework, okay, it gets launched into the air and blows up. Okay, that's not the movement that usually happens for most objects. Okay, at least you hope not. You don't throw a tennis ball in the air and it blows up midair. Okay, but guess what? Even with that explosion, it still behaves according to the center of mass. Okay, so imagine it didn't blow up for a second. It would get launched into the air and then fall back down to the earth, right? If it was a dud, it would just do that. Okay. Well, guess what? That explosion doesn't do anything to the movement according to Newtonian physics. If you took the center of mass of every little bit of ash and particle that got shot out from the firework, okay, guess what? You take where they all land and how they all move, they'd still land right here, the center of mass. Okay, assuming there's a lot of air resistance and stuff that causes problems. But if you did this in a vacuum or something, okay, they would still all land right where they should be, okay? Or the center of mass still lands where it should be for this scenario, okay? So that explosion doesn't change Newtonian physics. That center of mass will still land in the same spot it was supposed to, okay? That's pretty cool. Okay, one more example. Let's go back to the rolling cone. Okay, here's an aerial view of that cone. Okay, this is another person's ramp, but you can kind of see that the cone is bent in a specific way, okay? That makes it look like it's going to roll uphill. But if you notice, if you take the center of mass of that cone, okay, and you put that on the ramp, guess what? The center of mass is still going downhill. Even though the cone in general looks like it's rolling uphill on that ramp, okay, the center of mass is going downhill. And guess what? According to Newtonian physics, things should roll downhill, okay? So in reality, yeah, it looks like it's rolling uphill, but the center of mass is going downhill. Okay, and that's why it behaves that way. Okay? So overall, this is a key concept I want you to remember. Okay? The center of mass of any object will behave according to the principles of Newtonian physics. Okay? Newtonian physics isn't broken. We just have had this assumption that we didn't really point out that it's for the center of mass. Okay? Alrighty, but hopefully that made sense. Make sure you do the homework on center of mass, calculating the center of mass. Let me know if you have any questions, and thank you for watching.